Ladies and gentlemen, thank you for coming for this presentation. Covered another super tall building in China, Wuhan Greenland main tower. So it's about 600 meters tall. And when we design a high-rise building, and we team up with AIGG for this high-rise building, and also we design a kingdom tower more than 1 kilometer tall. So although this Wuhan Greenland Center project is not as tall as the tallest building in the world under design, but it really has a lot of unique feature that I like to cover today. And also I will emphasize how great architect can help structural engineer to achieve structural efficiency, how structural engineer can achieve the structural efficiency without hurting the architecture beauty, and how the structural engineer can simplify the curtain wall system to avoid the high construction cost. So first, let's start with the general information about the Greenland Wuhan main tower. So it's 600 meters tall, and when they finish, will be ranked the number 7th tallest building in the world. It's a mixed-use tower, features an office building, apartment building, and also a high-end hotel at the top. On the top of the building, you will see a special crown and a dome structure. So the owner is the Greenland Center Binjiang property, and the design team, we have ASGG as the design architect, structural engineer is Thornton Tomasetti, and positive energy practice as a mechanical engineer. And we have our S team, LDI ICATI, as the local design institute for this project and serve as the engineer of record. So this paper was contributed by myself and also a colleague from Dennis Pong and Mark Dannettel, and also we have Mark Dannettel and from ASGG.
Thank you, Paul. So thank you all. So working with our colleagues at TT, we understood that the wind was really controlling the issues in this building. And our firm at SCG, one thing we look at is these buildings as performance machines, very similar to what Mr. Wilkins spoke about early. We look at it like a car, like an airplane, like a machine that works, that functions to perform. So we looked at how can we deal with these wind issues, and how can we optimize the shape to be able to do these things. So there's 4 basic principles that we looked at. The first one, which we now understand, is the tapering of the building. By tapering that form, we know we're going to reduce the wind loads as the building gets higher, as we go up in space, and we smooth that shape out. So we take the program, which begins to reduce in lead spans as we go up into the space and create a smooth body out of that. The second thing is that we looked at rounding the top. We know the winds are stronger at the top. How we deal with the top of the building is a very important component of how the building performs in general. So we created this round top, what we call doming the top of the building. We learned that from previous jobs that we worked on, other projects that we've done, high-rise buildings, understanding how that really helps the shape of the building. And the third component, it's really kind of what we call the triangular floor plate, which we talked about on other projects before, and just softening the corners of the building, understanding that wind shedding, that vortex shedding as it goes around the corners, and how that really helps get the wind to go around the building and maximize the performance of the building. So all 3 of these are pretty common. We've seen in a lot of buildings. And then the 4th one is the one that we kind of introduced. We sing as well in Shanghai Financial Center, the top opening. But what we wanted to do is kind of bring that further into the building and find out how can we introduce more openings, work with the building or the shape of the building to kind of get the architecture, the structure, and the mechanical systems to all kind of work together and help optimize the systems.
This kind of building, and there's a very special curtain wall system. So we will ask help from our in-house structure engineer to solve how to simplify the curtain wall. So I will ask help from Mark Dannettel. He will present how to simplify this curtain wall system.
Thanks, Paul. So everyone here knows Dennis Poon. So everyone here knows that Thornton Tomasetti is a structural engineering firm. But what you may not know is we also have a building skin practice where we act as a facade consultant for the project. So in this case, it was very convenient for Juan to give us a call because, as you saw earlier when they were doing the wind tunnel tests, the building developed as a tapered form. And the tapered form develops warped surfaces which are no longer flat or planar. And the only way to do planar glass with that would be to do triangles, and most of us don't want to do triangular glass. So the problem of warped glass or warped curtain wall panels is that there's edge seals which tend to suffer damage when they are permanently warped into some position from a flat position. So initially when Juan called us, he asked us to use some parametric software such as Grasshopper to review the form of the skin of the building and basically do an evaluation to show which parts of the building could be done with flat glass and actually force it to be warped versus which areas may be too excessive of a warp and may be problematic. So this is one of those studies where the red areas were deemed to be excessive, just as an example. So we had to do a few activities. Commonly, one of the things that we need to do is we need to clean the geometry of the skin. And at the right, you can see that this is the revised plan at any particular level, where we actually revised all of the curves from the plan to actually be a single radius. So they're actually parts of a circle which have been combined to reconstitute the original plan. But we also did that in section. So over the height of the entire building, each X marks a point of a new arc. So it's a new portion of a circle. So all of these curves are perfectly tangential to each other, but we basically redefined the entire tower from circles rather than from the B-splines that are common with Rhino. And as we took the analysis forward, though, even with the clean geometries, from a constructability standpoint, we found that the warpage was still very excessive at the upper portions of the tower. So ultimately, we recommended rebuilding the skin by stepping back at each floor. So there's a slight step back and there's a misalignment from one floor to the next. And we developed everything with conical forms. So actually each floor, the glazing leans back towards the core, but then at each floor level it steps back in varying amounts, which allows for the differential warpage to occur. And then basically we use Grasshopper to reiterate and rebuild the entire form. And over on the right, you can see that each floor is kind of stepping back ever so slightly, but those step backs are, they vary along the entire perimeter of the floor. Thank you.
All right, so for this presentation, we emphasize that seamless coordination between the architect and the structure and also facade engineer. We can optimize architecture and the structure and also other discipline. And second, the special architectural feature can help the structural engineer to achieve the structural efficiency. And the last one, the structure optimization, and can add the special character to this architectural feature as well. So, thank you.